Okay, so let's start. In the previous class, I introduced this notion of the Lagrange dual of an optimization problem. All right. So firstly, we are assuming that we have an optimization problem of the following form, where you want to minimize some function f, subject to a bunch of inequality and equality constraints. Right. And the overall assumption is that all of these functions have some common domain D. More or less, we'll assume that the domain is Rn, but only in certain special cases we'll assume that it's different. And this optimization problem is assumed to have a solution, and the minimum value of f of x subject to these constraints is equal to p star. All right. And we also defined the feasible set or the constraint set, which is a set of all points in the domain or in Rn that satisfy all of the constraints, the inequality and equality constraints. Right? And for this, our end goal is, of course, to try and solve this optimization problem either by hand or numerically. But before that, I asked an even more preliminary question: is it possible to get non-trivial upper and lower bounds on p star? Because we observed that if you plug in any feasible point x into f, then you automatically get an upper bound for p star, a non-trivial upper bound. But a lower bound is not easy to get directly. So for this, I wanted to define another problem, which was the dual optimization problem. And in doing so, I defined the Lagrangian, which is essentially a linear combination of the objective function and the constraint functions. Right? And the coefficients of the linear combination are called the Lagrange multipliers. So for each inequality constraint, I have a Lagrange multiplier, and for each equality constraint, I have a Lagrange multiplier. So if the total number of constraints is, let's say, m plus n, then the total number of Lagrange multipliers is also m plus n. And using this, I define the Lagrange dual as the minimum of the Lagrangian, and this minimization is performed over the entire domain, or more generally over all of Rn. So this is not minimized only over the feasible set, but rather the entire domain of the function. All right. Now, as a side, the one way to assume that D is all of Rn is simply to look at the extended value function. So what you could do is, right.
When you say over the entire domain, that is with regard to x, right? So your lambda still remains element-wise greater than 0.
Yeah. That's that. For a given, because anyway the minimization is not performed over lambda, right? It's for a given lambda and given nu that you're performing this particular minimization. All right. I could just treat this as minimization over all of Rd simply by doing the following. So when I say that they have a common domain D, I could as well assume the extended value function for each of these f, f1, f2, and so on, so that they are well defined over all of Rd. Of course, it's an extended value function, so outside D it takes the value plus infinity, and inside D it takes whatever value that each of these fi's would take. So I might as well assume that D is, let's say, R to the something, R to the D, R to the little d, for example. All right. So we defined these two important notions. One was the Lagrangian, and the other was the Lagrange dual. All right. And using this, what we observed that the Lagrange dual is always gives you a lower bound on p star. Right? For every lambda greater than, that is element-wise greater than or equal to 0, and for every nu in Rn or m, the Lagrange dual gives you a lower bound on p star. So what you could do is try to get the best possible lower bound, or the closest possible lower bound, and try to maximize g of lambda and nu over lambda greater than or equal to 0 and nu in Rm. And the corresponding optimization problem is called the dual optimization problem. And this gives you some value d star, which is guaranteed to be less than or equal to p star. If d star happens to be equal to p star, then we say that this particular optimization problem satisfies strong duality. And hopefully, if the problem satisfies strong duality, then maybe there's an easier way of actually solving the original primal optimization problem. All right, that's the perspective that we will take. And we saw that there are some sufficient conditions for strong duality to hold. For instance, if the primal problem is convex and Slater's condition holds, then strong duality is automatically guaranteed to hold. All right, but there are instances of convex problems where strong duality does not hold, because in the case where it does not satisfy Slater's condition. And there are also non-convex problems where strong duality holds. So convexity is not necessary for strong duality to hold. That's the important point. Okay, and we saw a few simple examples. All right. So we'll continue looking at some basic examples in today's class, and essentially continue this discussion of duality, and hopefully, if I have enough time, towards the end of the class, I'll at least introduce a recipe for solving constrained optimization problems. Again, it's something that you've seen before, but perhaps not in the full generality. Okay, so let's look at another example. Again, I'll start with a simple example just so that we can get some more intuition. So let's assume that we have a simple one variable convex constrained optimization problem, which is to minimize say x square plus 2x plus 4 subject to the constraint that x square minus 4x is less than or equal to minus 3. Okay, so the objective function is quadratic and the constraint is also quadratic. Now, if you had to solve this, how would you go about doing it? I'm sorry?
Sketch a graph because it's only two variables.
Okay, do you even need to sketch a graph? This is all quadratic, right? You can, in fact, evaluate things. So firstly, it's you know that the minimizer can either be an interior point or it can be a boundary point. So when, in this case, what kind of an objective function do we have? It's quadratic and therefore convex. It's a smooth convex function, right? So when is the minimizer going to be an interior point of the constraint set? Yeah?
X belongs to 1, 2, 3.
X belongs to, I didn't understand. No, I'm asking a more basic question. So under what conditions will the minimizer be an interior point of the constraint set?
When it is the same as the global minimum over R.
Correct. So if it is a global minimum, so clearly if the global minimum or the global minimizer is an interior point, then the interior point is obviously then that point is also going to be the constrained minimum. Right? You agree with that point? If the global minimum belongs to the feasible set, then the local minimum will be equal to the global minimum. Let us now assume that the global minimum does not lie in the constraint set. It lies out somewhere outside the constraint set. Then what can you say about the minimizer, the constrained minimizer? Or I should say, constrained minimum. This is equal to the global minimum.
Point on boundary.
Yeah, and why so?
It's like the contrapositive of the statement. Like if it's an interior point, then the local minimum is the global minimum.
Yeah, if
It's an interior point,
okay,
and the function is convex.
okay.
Then
I've not said anything about the function. Okay, let's assume that the function is convex.
the local,
Okay, sure. Yeah, go ahead.
then the local minimum is the global minimum.
Why?
We said it before. Think
Correct.
Check the intersection points. Basically, like take the two graphs, the constraint one and the actual graph that you want to minimize,
Okay.
and check the points at which they both intersect. It can either be one or two.
I don't quite follow. What do you mean by what do you mean by the two intersecting?
Intersection of those two graphs.
Which two graphs?
The x square minus 4x plus 3 equal to 0 and x square plus 2x plus 4.
But why should you look at the point where they
Because
intersect?
if the slopes at both the points is positive, and given that it's a convex function, then it's only rising. So we can prove that it's the boundary point.
Okay, so one point is that you're right that the constraint minimum should be a boundary point. Okay, but my question is, why can't an interior point be the minimizer? And I'm not talking just with respect to this particular example. I'm talking about more generally. If you assume that the function is over Rn, yeah,
for the sake of contradiction, if you assume that it's in the relative interior,
okay.
then if you want to go towards the global minimum, then it can't be that the global minimum will be on the will be right next to this interior, the relative interior.
But if we draw a
That's
line,
not possible.
yes,
So it has
Okay,
to be.
let's go on. Yeah, go ahead.
Yeah, it can't be right next to the relative interior point. It has to be some non-zero distance away, and that would mean that when you go towards that, your function will become lower. So you just found a better point closer to the relative boundary.
Okay, but can you sort of prove things?
There exists always feasible direction.
Yeah.
There exists always feasible direction if it is interior.
Okay, so if you're in the relative interior or if you're in the interior, then every direction is a feasible direction.
Yeah.
Okay.
Yeah. So if you're in the relative interior,
Yeah.
there's the relative boundary and there's the outside where the global minimum is. There's those 3 points.
Okay.
If the interior really is the global minimum, I mean, no, if the interior point is a constrained minimum, then when you try to go towards the global minimum, you have to go through that relative boundary point, which would be a bit better.
Okay, but can you say all of this in the context of what we've already seen before?
Mean value theorem is
Not even mean value theorem.
intermediate value. Isn't it only true if it's convex?
so basically we can.
Yeah. So we're talking about convex functions, but over general.
So if we
Oh,
connect
horizontally.
the global minimum and the minimum inside the relative interior.
Okay.
Along that line,
Okay.
there will be at least one point which is inside the that set, but it should be greater than this value.
Okay.
Because it should be inside the relative interior, but it is greater than the value of the global minimum. So whatever listed also, whatever they're saying will be only true when both given are convex.
So I'm assuming that the objective function is convex.
Yes. Then what I said, take the two intersection points. Let's draw slope.
And again, I'm asking for something. It's a much simpler answer than all of this, right? Because it's something you have already seen before. for if an interior point has to be even a local minimum, what should it satisfy?
Should be less than or
Gradient zero.
It should satisfy the first order necessary condition, in which case the gradient should be equal to 0, right? And if the gradient is equal to 0, it's a convex function. If the gradient is equal to 0, then there's only one point where the gradient can be equal to 0, and that is at the global minimum. So if the global minimum is not an interior, it does not lie in the constraint set, then no interior point can satisfy the first order necessary conditions, and therefore it cannot be a constraint minimizer, because a constraint minimizer, after all, has to be a local minimum, right, within the constraint set. Is this okay? Okay, so now in this case, what would the global minimum be? Or the unconstrained minimum of this objective function, what is it equal to?
Minus 2.
Yeah,
Minus 2.
it's equal to minus 2. We just take the derivative and set it equal to 0, and that will be the derivative. Okay, it's not minus 2, right? So the derivative is 2x plus 2 equal to 0, right? So x equal to minus 1. Okay. I'm sorry? What is 3?
The minimum will be 3 unconstrained.
Let's, okay, sure. Unconstrained minimum is maybe it's 1 plus 4. Yeah, it will be 3. That's fine. So, in this case, what does the constraint set look like?
closed interval 1.
Yeah.
Closed 1.
And how do you find how did you arrive at this?
You send the minus 3 that side, so you will get
Correct.
x minus 8, x minus 1 is less than equal to 0.
Yes. So this is the same as x square minus 4x plus 3 equal to 0. Note that this is basically a quadratic upwards, right? So the function is going to look something like this. So basically, this region, the constraint set, would essentially be this particular region, right? Wherever the curve is below the x-axis. All right? And that happens to be the closed interval from 1 to 3. All right? So now,
Points need the constraint set to be convex.
I'm sorry?
The global minimum does not belong to the constraint set, the below points.
The global minimum, okay.
Does it require the constraint set to be convex?
So you can tell me, does it require the constraint set to be convex? It should satisfy the first order necessary conditions, right? I mean, so if a point, note that the objective function is convex, all right? So for any interior point, no matter what the constraint set is, for any interior point to be a local minimum, the gradient should be equal to 0, and that can't happen. Right? Okay. So coming back to the example, so I want to minimize this x square plus 2x plus 4, and the corresponding constraint set happens to be the interval from 1 to 3.
So is it like closest point to the unconstrained minimum?
Okay, so that's one way to you can try to guess. So where is the global minimum? It's at -1, all right? So the function looks something like this. Minimum value is 3. So this is x, this is -1, all right? And the interval is 1 to 3, all right? That's the constraint set. This is my constraint set. So where do you think the minimum will lie? It has to be at x equal to 1 because it's a convex function and the constraint set is to the right of the unconstrained minimum. So therefore, to the right of the unconstrained minimum, the function is increasing, and therefore the minimum value will occur at x equal to 1. Okay. So even for this simple example, we had to use quite a bit of geometry to guess what the minimum is and arrive at the solution. All right. Okay, so now so this is the primal problem. This is the primal optimization problem. Let's try to construct the dual and see if that's any simpler to solve, any easier to solve. Okay, so let's start with the Lagrangian. How many constraints do I have? One inequality constraint. So what is the Lagrangian going to be equal to? Yeah? It's x squared plus 2x plus 4 plus lambda times x squared minus 4x plus 3. Right, okay. So let me sort of group together the coefficients of x squared, x, and the constants together because it will make things easier. So this is 1 plus lambda times x squared plus 2 minus 4 lambda times x plus 4 plus 3 lambda. And the Lagrange dual is going to be the infimum over all x in R of L of x comma lambda. Right? Now, is L of x comma lambda, okay, so what is the infimum going to be equal to? How will you find the minimum? Okay, so take the derivative. Are you sure that you can do it in this case? And why can you do it in this case?
It's a quadratic function of
Like x belongs to R.
Quadratic is not enough.
convex.
Yeah, it's a convex quadratic. It's not a concave quadratic. You have to be careful, right? Because for instance, if the coefficient of x square could be negative, then things don't go, you can't make the same conclusion. All right. In this case, the coefficient of x square is always going to be positive because we're assuming that lambda is greater than or equal to 0, and therefore I can just go ahead and do this. Okay, so this is.
So in the other case, the infimum doesn't exist.
Then you have to be careful. Then you have to sort of look at it case by case. The infimum would be minus infinity potentially in some regime of lambda. Right? That's why it's important to be very, very careful.
But it isn't possible, right?
Why not?
For L of x comma lambda to be non-convex. If the objective function and the constraints are.
Okay, so again, I may be going a little back and forth between whether a function is convex or not. In general, unless I say so, the objective function and these constraint functions need not be convex. Okay?
In which case you won't use this.
I could, right? That's the point. So there can be non-convex functions for which or non-convex problems for which strong duality does hold. Right? That was the point that I tried to make.
But
So
how do you verify that's the minimum?
which one?
When strong duality holds,
Uh-huh.
how do you know that that is the minimum value?
In general, you don't, but I can still use this approach to at least get a lower bound on the minimum, right? If I know that strong duality holds, then that should be the minimum, right? So if I have a non-convex problem where strong duality holds, somebody tells you that for this particular problem strong duality holds, then, and I'm somehow able to solve the dual problem, then the solution or the maximum value, the constrained maximum that you get from the dual problem, that is going to be equal to P star, even if the primal problem is non-convex. All right. So you can use this whole approach even if the problem is not convex. But then you have to be careful because you don't know. If you know that strong duality holds, then fine. If not, then all you can conclude is that it's a lower bound. Okay. But at the moment, we are just trying to investigate what the dual optimization problem looks like. Okay. Okay, great. So what is G of lambda going to be? So let's assume that I set the derivative of L of x comma lambda with respect to x to be equal to 0. Then what is the minimizing x going to be equal to? Yeah, so this whatever x prime, let me call it x prime, this is equal to 2 lambda minus 1 divided by lambda plus 1 or 1 plus lambda. Right? So what is G of lambda? Because after all, that's what I'm interested in. It's going to be 2 lambda minus 1 the whole square divided by 1 plus lambda plus 2 into 1 minus 2 into 1 minus 2 lambda. So that happens to be minus 2 times 2 lambda minus 1 the whole square divided by 1 plus lambda plus 4 plus 3 lambda. This will just be minus 2 lambda minus 1 the whole square by 1 plus lambda plus 4 plus 3 lambda. Now you can go ahead and simplify this. It's no longer just a simple quadratic. Okay. So you have some quadratic in lambda divided by 1 plus lambda. Okay, so it somehow seems to be more complicated in the problem that I started out with. But of course, this is under the constraint that lambda is greater than or equal to 0. But again, in this case, do you think strong duality holds? Why? The objective function is convex and you want Slater's condition to be satisfied. So there should be some interior point for which the constraint is satisfied with the strict inequality, and that happens.
0.
Right? So you take any point strictly between 1 and 3. That's good enough. All right. So let's just quickly see what this looks like. So over here, right, the blue curve. Okay, maybe I'll try to save this. Okay. this out, but okay. So I'm not sure if you can see it clearly, where that the region that we're interested in is the interval from 1 to 3. Right? The blue curve essentially represents the objective function. Okay? And the minimum value of the constrained minimum P star, that's indicated in the green line at the top. So maybe let's three. Yeah. So the blue curve essentially represents the primal objective function. Okay. And the minimum is basically attained at x equal to 1. In the same plot, in this case, the dual optimization problem also happens to be univariate. But you shouldn't mix up the two variables. The dual variable is different from the primal variable, right? So in general, I can't just plot the two in the same figure, but just for convenience, I'm representing both in the same figure.
So the dual is lambda. The x-axis is
Correct,
lambda.
correct. So I'm using both the x-axis and lambda axis to be the same. Okay, and so the brown curve represents the dual function for lambda greater than or equal to 0. You see that it's first increasing and then decreasing. It's a nice concave function. Okay, but the maximizer of the dual happens to be or the maximum value of the dual function happens to be equal to the constrained minimum of the primal function. Right? So d star is equal to p star as expected, because this is a case where strong duality actually holds. Okay, but it doesn't mean that it's become any simpler, right? But the nice thing in this particular example is that the minimizer is an interior point of the dual feasible set, right, as we saw in the figure. So in principle, I could just take the derivative with respect to lambda, set it equal to 0, and I would actually get the answer.
The dual feasible set is entire R.
No, the dual set is all lambda greater than or equal to 0. So it's a much simpler, the dual feasible set is actually much simpler than the primal feasible set. It's always going to be something simple. Correct? Okay. Okay.
But it is still infinite in one direction, right? Doesn't it make it hard for and bounded in one?
It's bounded in one direction, but sometimes, as we'll see a different recipe for actually solving constrained problems. Right now, we're just trying to get some intuition as to what the dual looks like. Okay. All right. So let's do one more example, a slightly more general example. Suppose somebody gives you a linear program. What does the dual look like? Okay. So in the previous example, what we saw a quadratic optimization problem. The primal was a quadratic program with a quadratic constraint, but the dual program was something that was not quadratic. Okay, so this can happen. But let's say that I have a linear program where I want to minimize, say, C transpose X subject to the constraint that some matrix A times X is less than or equal to B. Okay, so it's a linear program of this particular form where A is some M by D matrix and C and X are in RD, B is in RM. Okay, so let me just bring this down to standard form. I want to minimize C transpose X subject to the constraint that AX minus B is component wise less than or equal to 0. This is the same as saying that if I take the ith row of A, then AI times X minus BI is less than or equal to 0. Here A is a row vector. Right? Let's go ahead and try to compute the Lagrangian. This is equal to C transpose X plus, I can write this as lambda transpose AX minus B. Right? Do you agree with me? Okay, great. Again, let me bring all of the terms that involve X together. So this is C transpose, or the terms involving X are the C transpose X and this, right? So I can write this as C plus A transpose lambda transpose X minus P transpose lambda. Okay, is this fine? All right. What can you say about the infimum in this case? Okay, minus infinity always.
Provided that C plus A transpose lambda is not equal to 0.
Exactly. So if this quantity is non-zero, then the minimum is going to be minus infinity. The infimum is going to be minus infinity. All right. If it's equal to 0, then maybe not. All right.
I mean, if it is identically 0, it's B transpose lambda, right?
Correct. Exactly. Right. So it's equal to minus B transpose lambda if A transpose lambda plus C equal to 0. And it's equal to minus infinity else. Right, so this is the dual function. So this is an extended value function, of course, because it's allowed to take values plus infinity or minus infinity in some regions. All right. So now what is the dual program? My goal is to maximize g of lambda. So what would it be? What would the dual program look like? Yeah. Yes. Why is it minus infinity? Okay. So suppose that this whole quantity over here is non-zero. Let's call it some vector u. Okay. So suppose I have something of the form u transpose x minus some alpha. I want to know what is the minimum value that this can take. Okay, my claim is that it can take that the minimum of this is minus infinity. All right. One way to see why that is the case, again, we can try to play the trick that we did in the previous class for a slightly different problem. So x is allowed to take any value, right? So suppose I take x to be equal to some t times. Okay, so firstly, this u transpose x minus alpha is greater than or equal to minus infinity. That's a trivial fact, right? So x, let's take x to be equal to t times u. Okay, and let me try to take the infimum over all t of L of t times u comma lambda. All right. What is that equal to? That's equal to minus infinity. And so I'm performing this minimization over a constraint set. So the minimum can only be smaller, but it can't get any smaller than this. Right? So the minimum is equal to minus infinity. Okay. Is that clear? Any questions? Okay, so this is my.
I didn't understand why you have this two cases here.
Okay.
Because this is over the entire space of lambda, right? Now.
Lambda component twice greater than or equal to 0.
Right. So that.
Yeah.
Possible.
Exactly. Yeah.
Now, in there, G is kind of a surface, right?
G is going to be a surface.
But
Sure.
it's parameterized on A transpose and C. Is what you're saying?
No, as I say, so G is basically an extended value function, right? So what will it look like? In some sense, it's going to look like this. Suppose I had to sort of draw it in 3D. I have two variables and this is the value of the function. Then in some region, it's going to take some finite value, right? Everywhere else, it is minus infinity, right? So right, so everywhere outside this region, it's all minus infinity.
Because there's also that hidden player X behind the scenes.
So we've taken out x, right? We've taken out
by
x.
doing the infimum, and it could turn out that in that process it is minus infinity in some cases. Some cases it is not.
Correct, exactly. Right. So again, this is an extended value function, which is in principle supposed to be. So there are two ways of looking at this. One way of interpreting this is that g of lambda is only defined when A transpose lambda plus c is equal to 0, because it's a valid function, because the infimum exists only when A transpose lambda plus c is equal to 0. Right? And outside, if A transpose lambda plus c is not equal to 0, then g of lambda is simply not defined. So the correct state, that is really the correct mathematical statement. But then we are looking at this as an extended value function. So wherever it is not defined, we say that the value is minus infinity. Because we are allowing the function to take values plus infinity or minus infinity, as it's an extended value function. Okay, does that make sense? All right. So now what is the dual optimization problem? The dual optimization problem is basically maximize g of lambda subject to the constraint that lambda is greater than or equal to 0 component wise. But in this case, what does it reduce to? Is it even necessary to take this particular constraint? No, right? Because the maximum value would obviously be attained somewhere over here, because it takes finite values in that region, and if A transpose lambda plus C is not equal to 0, then it takes the value minus infinity. So it's enough to just look at this particular set to maximize this. So that turns out to be maximize. So what is the dual objective in that condition?
May happen that A transpose lambda plus C is never equal to 0.
What do you mean? Oh, you mean depending on A and C?
Yeah, dependent.
Yeah, that's perfectly possible, right? It's possible that no point is so-called dual feasible, in which case the maximum is minus infinity. So it gives you a trivial lower bound on P star. But as long as there is at least one dual feasible point, you get something non-trivial. So the maximize minus B transpose lambda subject to the constraint that A transpose lambda plus C equal to 0 or A transpose lambda equal to minus C and lambda is component wise greater than or equal to 0. So the dual of a linear program is another linear program, because even in this case the objective function is linear in lambda and the constraints are also linear in lambda. Okay, so that's a very important fact. The dual of a linear program is also another linear program. This does not hold in general, because just in the previous example we saw that the dual of a quadratic program with quadratic constraints need not be a quadratic program. But suppose that you have a quadratic program with linear constraints, then you'll again get a quadratic. So I leave this as a homework. So I will take a special quadratic program. So minimize say norm x square subject to the constraint that Ax equal to B. All right. So what is this has a nice geometric interpretation. What does this set Ax equal to B correspond to? Yeah? It's a set of all x such that Ax is equal to B. What kind of a set is this? Is it a polyhedron? It's just some affine set. All right. So you're given the affine set f equal to Ax is equal to B, right? And in a sense you're right, it is a polyhedron. It's not a polytope.
Need not be bounded.
Need not be bounded, of course. In general, will it ever be bounded?
Can be bounded, but You could have it such that only something like A transpose X.
Correct. It could be bounded, but in general, it's going to be a polyhedron. All right. Okay.
A invertible is bounded, right?
If A is invertible, of course, it is bounded. In that case, you just get 1 point. Okay? It's just a singleton set. All right. So now, what does this correspond to? What does this optimization problem correspond to? Can you describe it geometrically?
What is the
So this is the optimization problem, right? This is the optimization problem. How would you geometrically describe this optimization
So
problem?
if you have a Bx equals Bk,
You have Ax equal to B, you have the set F.
just some distance away from the origin.
Correct.
Now you take this sphere, take a sphere, and then you keep condensing the radius until the plane just becomes a tangent. Now that distance is the minimum distance.
Correct. But there's a slightly simpler way of saying exactly what you said.
Yeah.
Is the minimum distance to...
Perpendicular distance.
Correct. It's the distance between the origin and the set. Right? So the problem is basically to find the minimum distance from the origin to F. Right? And if you think about it, I made a sort of, just as a passing comment when I talked about projected gradient descent, where I said that you could run gradient descent, but at the end of each step, you sort of project it back to the constraint set. That is, you're given an arbitrary point, let's say you run gradient descent, you get the current iterate, you find the closest point within your constraint to this particular iterate, and you treat that as your next iterate. And you keep doing this, right? So if I'm able to solve problems of this particular form, right, I could basically replace this norm x square by some norm x minus a the whole square, right? Which would be the closest point from F to this, or the closest point from the vector A to this particular set F. Right. So every time you want to run something like projected gradient descent, in each step you want to solve an optimization problem of this particular form. All right. So that's why this particular problem is useful. If your constraint set is linear, then this is the kind of sub-routine that you would need to run in each step of projected gradient descent. Okay, so in this case, it so happens that the dual optimization problem is also another quadratic. All right. Find the dual optimization problem. And then also what you can do is try to see what happens numerically. So just assume that, first find the general form of the dual optimization problem. For general A, B. And then just try to plot the primal objective function. Find the constraint set also. Take A equal to 1, 1, 2, 2. B equal to 1, 2, and try to plot the primal objective as well as the dual objective. Okay, any questions? Okay, so far again I have not simplified the problem of solving the optimization problem, right? I had a primal optimization problem. I defined the dual optimization problem, but it didn't seem like the dual optimization problem was ever easier to solve than the primal optimization problem. It always looked like it was more complicated than the primal, right? But so now I'll just give you a recipe, something again that you would have seen earlier in your previous courses. I'll just state the recipe and then we'll see how we get this particular recipe of finding the solution. All right. The recipe is based on these conditions by Karush, Kern and Tucker. And the claim is that if you want to solve a constrained optimization problem, it's enough to just find the solution to a system of equations. Equations are not linear, they're in general going to be a non-linear system. But in many cases, it turns out just by solving for this system of equations, you can get a closed form expression for the solution. And indeed, we'll see some examples where we can find closed form expressions. All right, so all of this is under the assumption that strong duality holds. If strong duality does not hold, then this whole approach is not particularly helpful. All right. Basically, the KKT conditions are the following set of conditions. So they give you a set of equations and you try to solve for them. So we say that x star, lambda star and nu star. So I'm trying to jointly solve for both the primal and the dual optimization problem in some sense. All right, so this tuple satisfies the KKT conditions if basically it should satisfy primal feasibility, so Fi of x star is less than or equal to 0 for I equal to 1, 2, 3 up to n. Hj of x star is equal to 0 for j equal to 1, 2, 3 up to m. It should satisfy dual feasibility. Let me move this. Which is just that lambda star should be component wise greater than or equal to 0. Right, the third requirement is that it satisfies stationarity. That is the gradient of the Lagrangian evaluated at x star, lambda star, nu star, this should be equal to 0. So take the partial derivatives with respect to each xi, each lambda I, and each nu I. They should all be equal to 0. Okay, this is more or less, this is kind of expected, but the most subtle and perhaps one of the most important conditions is the so-called complementary slackness condition. Which says that for I equal to 1, 2, 3 up to n, lambda I star fi of x star should be equal to 0. So remember that lambda I should either be greater than or equal to 0 or fi of x. So if you just look at primal and dual feasibility, each lambda I should be greater than or equal to 0 and fi of x should be less than or equal to 0. But what the complementary slackness condition says is that suppose that lambda is strictly greater than 0, then fi of x star should be equal to 0. Alright? So if you have slackness in one of these, then you cannot have slackness in the other. Alright? If fi of x star is less than 0, then lambda I should be equal to 0. Only then is it an actual optimizer. Alright? Right now I've not said why this is the case, but let's assume that this is what it is. The claim is that if the primal optimization problem satisfies strong duality, irrespective of whether it is convex or not, if I'm somehow able to solve for these KKT conditions, then I get a solution not just for the primal optimization problem, but also for the dual optimization problem. All right, does that make sense? So just as a very sort of toy example, let's take the problem that we had earlier, one of the first problems that we considered of, let's say, minimizing x square such that x lies in the interval from 1 to 2. Okay, this is equivalent to minimizing x square such that x is less than or equal to 1 or x minus 1 is less than or equal to 0, and minus or 2 minus x is less than or equal to 0. Question? Right? Question? So this is, yeah? I'm sorry, yeah. Sorry, x minus 2 is less than or equal to 0 and 1 minus x is less than or equal to 0. That's right. Correct? Okay. Now, I have two Lagrange multipliers, lambda 1 and lambda 2. Let me just try to solve for this. The primal and dual feasibility conditions don't give me anything very interesting. What is a Lagrangian equal to? L of x lambda 1 lambda 2 is equal to x square plus lambda 1 times x minus 2 plus lambda 2 times 1 minus x. All right. I need to solve for the KKT conditions now. The interesting KKT conditions are in this case happen to be stationarity and complementary slackness. So stationarity says that the gradient should be equal to 0. What is the partial derivative of this with respect to x? I get stationarity implies that 2x plus lambda 1 minus lambda 2 is equal to 0, or x equals lambda 2 minus lambda 1 by 2. And complementary slackness tells me that lambda 1 times x minus 2 is equal to 0. Perhaps I should say x star equal to 0, or lambda 2 star times 1 minus x star is equal to 0. So effectively, again, it seems like overkill for this very simple problem, but if you look at this, effectively all I have is just a system of linear equations which I can solve. Right? All I have to do is just solve for this system of equations. Or another way to do it I can just plug in this particular value of x star into this and solve for it. But the complementary slackness conditions also tell us something, because either x is, so if x is a boundary point, then exactly one of these conditions have to be satisfied. And if you try to investigate it a little further, in this case we know that the minimum is achieved at x equal to 1. So 1 minus x star will be equal to 0. Lambda 2 will be non-zero, strictly non-zero. Lambda 1 star will be equal to 0, and x star will be or x star minus 2 will be non-zero. One way to get that is, we know that x star should be between 1 and 2, right? Because it has to satisfy the primal feasibility constraints. So in any case, this lambda 2 star minus lambda 1 star divided by 2 should be greater than or equal to 0. Right? Or lambda 2 should be greater than lambda 1. All right. So again, even in this seems like a simple example, but this whole process seems quite complicated. Right? I don't see, it doesn't look like I've simplified the problem at all. But in the next class, we'll see some more examples where you'll really see the difference that these KKT conditions can make. You can exactly solve for the KKT conditions and get a closed form expression for the solution. Okay? All right. So in the last few minutes, we're going to have a quick quiz. Yeah, question. Minimize normal. Okay. Previous example, yes. Such that AX is equal to B. Why do you think it's the solution the same as the least squares?
You can select a point on AX equal to B, and
Okay.
you're trying to minimize the distance between it.
Okay. So that's why I want you to find the dual program and then ask that question.